Finally, there's an experiment about superstructure. All right, here's what I mean by that. So you have structures, which might be text, strings, numbers, little pictures of trees, and you have your combinatorial sequence that counts how many there are for each n. But now I want to take that set counted by, and I gave you which size to pick, same size as you drew at the beginning, and see if you can organize a bigger structure on those. There's an awful lot of possibilities here. The simplest one would probably be a way to order your set in a row from smallest to largest. And that means you could, if you had pure numbers, you could just order it from smallest to largest or largest to smallest based on something about the number itself. You know, look at the size, or write them how they would show up in a dictionary, or something like that. I decided to go with something a little bit fancier in here, which might turn out to be easier for some of your projects. And that is, instead of an ordering from smallest to largest in a row, it's a superstructure that involves networking your smaller structures. So I define a rule for connecting two insertions of n pairs of parentheses in a word of n plus 1 letters. And if you write down all of those structures for a certain n on the page, and then follow this superstructure rule, what you'll have is a picture with a bunch of parenthesizations, and some of them will be connected by lines. And that creates the structure of a combinatorial graph. So for each pair, looks like I defined it on trees first, and then I moved it over to the pairs of parentheses. That's what the instructions say. Define it on one small structure, or one small set of structures, which is, in our case, a sub 3, which came out to 4 or 5 pictures. There's 4 leaves, 5 pictures. And here's the rule that I said. First, for each pair of binary trees, connect them with an edge, just a line, if and only if there is a single branch point for which the next branch above it changes its attachment from left to right. So you can take 2 pictures of a tree, and they're different only by zooming in on one branch point, and the branch that's on the left of it switches to the branch that's on the right of it, like in that little picture. Inside of a zoom looks like that. So let's look at some at the 5 trees. So there's the 5 trees on the left. So if you look at any 2 of them that are connected by a line, the only difference between those 2, like the very top one, I've taken the second branch, or the branch that goes to the second leaf, and I've switched it from pointing left to pointing right across that branch point just below it. And then that gave me the tree that's just to the left of the top tree. And when I connected all the pairs of trees that had that property, that were almost the same except for one branch switching left to right, it joined up into a circle, like a pentagon, actually. And that just happens, and it won't happen for everybody's. If you make up a rule of how to connect pairs, you might get a star shape, or you might get like a complete graph where every single pair is attached to every other, or every single structure is attached to every other single structure. But it doesn't matter. It's completely experimental. So you get to make up the rule of how to order them in a line, or how to connect them with lines. Another possibility would be making sort of a clustered structure on them, where some of them get circled and others don't. You can make a Venn diagram out of them. That's a superstructure too. So the next thing that you're supposed to do is, once you've figured out what that superstructure is on one set, and it can be anything, it's completely creative here, then you show it on the other set, the other structures, so via the bijection. Now this bijection works because it's the one that we observed on the small set. It was the rule we made up for the small set that worked. We don't know if it works on the big set, so we're not going to bother doing that. That might work for some people and it might work for other people. But for the small set, we knew the bijection worked, and here's the corresponding parenthesization for each of those trees. Just to see where they landed. And then you can see that if you look at those parenthesizations on the right there, the moving a tree branch over corresponds to shifting parentheses around. But you don't have to figure that out. It just happens to be something that you notice here. Then finally it says for each of you to transfer the superstructure that you used for n equals 3. Oh, sorry, for whatever your smaller n value is, onto the other structure first. But then it says to use the first structure that you picked, in this case it would be the trees for me, because I made up a rule for connecting those, and see what happens on the next size set. So my rule for trees was to connect the ones they're only different by moving a branch, and then I took the 14 trees and connected the ones with a line that were only different by moving a branch. And there's all the lines that we got. It has a bunch of little pentagons and squares connected together. If your superstructure on the small set was to put them all in a line, then you can try to do that on the large set. Use the same rule to put the large set all in a straight line, largest to smallest or something like that. And this is another experiment. It may turn out that you can't figure out whether to connect. There may be some question marks, or you can't figure out which order they should go in. There may be some question marks. So the instructions just say to try it. If you can always figure out exactly which ones to connect, which ones to cluster in a Venn diagram, or which ones to order in a line from largest to smallest, that's great. And if you can't, you can have some question marks that say, I don't know, can't figure out which way, how this superstructure would extend to the bigger set. That's the experiment.